All right, so in this lecture, we're going to take a look at categorical data, thanks to Professor GS, who many of you will probably have for machine learning in the next semester. So categorical data we've talked about. We have a limited number of discrete values, such as eye color, blood type, product type, dog breed, what have you. Categorical data is very important to being able to do statistical analysis, but of course you can't do math on categories. So we have to have other techniques for dealing with categorical data. Humans can often immediately recognize associations and relationships among different categories that are invisible or indistinguishable for the computer or the algorithm. For example, if we had a city column in our data and values in here included New York, New Jersey, New Delhi, we would know that New York and New Jersey are geographically near each other and in the same country and probably quite similar to one another in various ways. New Delhi is on a different continent in a different country. But of course, without an awful lot of additional geographical data, that won't be apparent to your computer algorithm. There are two different varieties of categorical data. There is nominal data, where there is no apparent ordering, such as eye color, dog breed, gender, what have you. And then there is ordinal data, where there is an inherent ordering, although we have to tell the algorithm, tell our code what that is. And this would include things like, the gold, silver, and bronze medal rankings in the Olympics, for example. Now, pandas, we haven't seen this before, actually has a categorical type that we can apply to columns of categorical data. And we can use ordinal categorical types as well, so that we can tell the difference in rank between values in an ordinal categorical type. Okay, so for example, if we define an ordinal categorical type, not only will we be able to tell the difference between values, but we'll also be able to sort the values and figure out minimum and maximum values in columns of these ordinal categorical values. Let's see how that goes. Okay, and this will work both in series and data frames. Here is a series of strings representing eye colors. Well, representing colors, period. So we've got blue, green, blue, brown, gray, brown, brown. And if we display the series, here's what we get. Notice that by default, these things are simply recognized as objects. If we ask for a description of this series, we get told that there are 7 items in the series. There are 4 unique types. The top type, in terms of number of occurrences, is brown, okay? And there are 3 brown values. Here we have a histogram, which for a series you can get a histogram just by saying s.hist. The semicolon there is unnecessary. And we might need to do a plot.show to see this thing on the screen. Here I am adding the D type of category to the series. So I'm basically defining the series in the same way, blue, green, blue, brown, gray, brown, brown. But instead of allowing the default data type of object to be applied to the items in this series, I'm saying category. And now these things are recognized as separate categories. There are 4 separate categories, blue, brown, green, and gray. If I now ask for a description, I get basically the same description that I saw before. There are 7 values. There are 4 unique values. The one that occurs the most often is brown, and that occurs with a frequency of 3. We can ask for the values within the series, and in this case, not only will we see the list of the values, but we'll also be told that these values have a category data type. And we can ask for the categories. Okay, so s.values.categories will show us the categories, and this is stored as an index. The category names themselves, although they're strings, are just stored as objects. The default storage mechanism for string values in series and data frames. It may or may not be interesting to know that there are numeric codes associated with these different categories. Now, these numeric codes turn out to be useful to save space when you're doing machine learning algorithms, but we've got arbitrary numerical codes applied to these different categories. So blue is 0, brown, so blue is 0, green is 1. Green is 2. Oh, of course. These are the indices within the index, my mistake. So we've got blue, green, that's index sub 2, blue, brown, gray, and brown and brown. So using these integer values to represent categories both saves space and increases efficiency in various things like machine learning algorithms. Okay. I can, instead of creating a series and specifying its data type as categorical, I can simply create a categorical data type directly. I can give the values in this for this service ratings object, and I can also specify what the categories are. Here I've just got one value of each category, so the list of values and the list of categories is the same. And notice that here I'm specifying that these are ordered, okay? So very dissatisfied is the lowest value, up to very satisfied, which is the highest value. This enables me, notice when I ask to see that thing, I get told these are the specific values that are currently in that service ratings object, and there are 5 categories, and notice that these things now are ordered because I said I wanted them to be treated as ordered. And once again, here we have the categories associated with that service ratings object. If I ask for as ordered, then they come out. This is not very illuminating, I guess, because the thing was originally defined in order anyway. So if I ask for them as ordered, the values come out as ordered. Okay, we've got the lowest value up to the higher values, and once again I get told what the ordering of the categories is. Okay, and just as we saw previously, these are actually stored internally as integer codes, 0 through 4. Okay, so given our categorical object, service ratings here, we can wrap that into a series, and then we can access the categorical information within that categorized series using the cat accessor. So s.cat.codes will give me the values of the codes. s.cat.categories will give me the values of the categories. Let me just back up momentarily here. So notice that in the service ratings here, there are no, we have values, we have categories, we don't have any labels applied to those values. They just exist in a list or an index. By putting that into a series, now we have row labels associated with the codes or with the categories. Okay, and if we sort the values, because this series has ordered categories, the values come out in ascending order. Okay, and again, it's a little dissatisfying because the whole thing was defined in this order in the first place. Let's look at a value that's a little more varied, if you will. This time, we're creating the series directly, and we're using something called the categorical D-type to describe the categories in use for the values in this series. This is equivalent to creating the categorical object first and then putting that categorical object into the series. So here in this series, we've got, what have we got? 8 values: very dissatisfied, very dissatisfied, dissatisfied, very satisfied, neutral, very satisfied. So we've got 8 values. We've got the same 5 categories, and these are ordered. Okay? So now, if we ask to see the contents of the series, the values, the row labels are in the same order in which these values were defined. And I'm told that that the data type of these things is categorical with this order. So if I do a sort, now I get the values in ascending order according to the ordering of the categories. And you'll notice that the row labels get changed around to reflect that new ordering. So very dissatisfied, twice, dissatisfied, neutral, neutral, satisfied, very satisfied. Cool. I can access the codes within S the same way I did before by saying s.cat and the codes. And I can also find out the names of the categories associated with these cat codes. Well, the cat codes. The cat codes are for each value within the series. And the actual categories are 0, 1, 2, 3, 4 for the different levels of satisfaction. All right, so now let's take a look at categorical data stored in data frames. Of course, the data frame is a collection of columns, and each one of these columns is a series, so there's going to be a lot of similar behavior, obviously. Here we have an example of a small data frame. We're using a dictionary to construct this data frame, And there are two key value pairs in here. Name is the name of the person, and eye color is the eye color. So name is, well, I suppose it could be categorical, but we're just thinking of as unique labels for people. And then the eye color is the category here. From here out, as the examples become more intricate, I want to actually do these things in Python directly. So let me copy and paste that over into my Python environment here. I have already imported the necessary modules: NumPy, pandas, matplotlib.pyplot. I've also imported Seaborn. We're going to start seeing some examples with Seaborn in this material. And I have made it so that columns are not suppressed when I display a data frame. All right, so here I am copying in this data frame, and when we display the data frame, the row labels are the default 0 through 4, and we have the name column and the eye color column. Okay, so the D types of all the of both of the columns here are object. They're strings. All right, so if I ask for df's D types, I see that they are objects, and I want to convert that eye color to categorical, which I can do in this way. All right, we're going to use the as type method and give category as the new data type that we want, or the data type that we want to convert eye colors into, and store that back into the eye color column. So let's do that. So we're going to say df sub eye color gets df sub eye color as type category. And now that I've done that and I ask for the D types again, I see that the eye color is now a category rather than an object. And I can look at the values, and I can see the categories associated with those values. All right, so df sub eye color dot values, and because these are categorical now, I can ask for the categories associated with those values, and I just get the index representing those values. All right. If we ask for the value counts of eye color, there are only 3 different eye colors currently: brown, blue, and green. And we have 3 brown, 1 blue, 1 green, as we can see here. Okay, so John, Jane, and Rose have brown eyes. Robert has blue. Mary has green. df sub eye color dot value counts. Alrighty. We can look at the, if we look at the values, we will get back the individual values, and then if we look at the codes, we'll get the numeric codes corresponding to each of those values. These value codes are these small integer values, right? So df sub eye color dot values is brown, blue, brown, green, whatever. And if we look at the codes, we see the corresponding small integer values. Now for eye color, there is no natural ordering. We can define ordering for a column in a data frame, but we need to make sure that the object type is able to be ordered. So let's add a competition place column to our data frame that will originally be given a data type of object, but we can revise the data type to an ordered categorical type as we did previously with the series example that we saw. So let's try these things out. We're going to add a competition place column to our data frame, and that is going to receive the values second, first, second, fourth, fifth, second. Oh, I'm being silly here, right? I can just copy second, first, second, fourth, fifth. An extra comma in here. There we go. Okay, so there's the modified DF with that additional column and the D types. We do have category for eye color, but at this point just object for competition place. We don't want to just turn competition place into an ordinary category, because we do want to define an ordering for these for second, third, fourth, fifth places. There is no third place person in here, but that's okay. We can still define a third place category, even though we don't currently have any value for that. Okay, so here, notice we're setting first, second, third, fourth, fifth as an ordered categorical type for competition place. So let me copy and paste this over. I need to say that categorical D type is defined in the pandas module. There we go. Okay, and here's our modified data frame. Actually, at this level, it doesn't look any different. But if I ask for the D types, all right, I get told the competition place is a category now. And if I ask for if I ask whether this category is ordered, df sub I get told that that is true. Whereas if I ask whether eye color is ordered, it's not. All right? Here are the numeric codes associated with those with that ordering. Okay? df sub, let me copy and paste here. copy up to cat. And here's the values. Whoops, my mistake. I meant to ask for the categories. Let me try that again. Okay, and there we go. And the codes. Alrighty. If we ask for the D types, we do see that competition place is now categorical. And if we ask for a description, we get told for each of the columns how many values, well, how many rows there are, basically, how many unique values there are, and what the top value is. Now, for name, where the names are unique, we just arbitrarily get back the first name. Eye color occurs 3 times, so we get it back, and second place occurs twice, so we get it back as the top competition, as the most common competition place. Let's give these things a try. Okay, so df.d types, df.describe. And there we are. Now, because that competition place column is ordered, we can invoke the sort values method on competition place. So df sub competition place. Okay, that's the current ordering, second, first, second, fourth, fifth. And if we ask this to be sorted by values, we get first, second, second, fourth, fifth. And of course, we can see the entire data frame sorted on that field. So df.sort values by competition place. There we go. All right, so now we have the whole data frame sorted in order by competition place. That, of course, does not directly change df. It returns to us a modified copy of df. This is one of these places where we could use the in-place equals true to cause that to happen immediately. Let's do that. Let me add the in-place equal true keyword argument, and now df is sorted in ascending order by competition place. All right, now we're going to take a look at a much more intricate, larger data frame here. This data frame has various string columns, hourly rate column, which is floating point values, and an age column, which is integers. Let me go ahead and copy and paste this huge thing. I notice that some of the names go off the side of the screen here, so I'll have to patch that up. Copy that in. And okay, so fortunately, the stuff that was off the right side of the visible part of the window there did get copied anyway. And so here's my data frame. All right, name, eye color, gender, hourly rate, remote worker, yes or no, and age. Now I would like to group these ages into categories, And because ages is a naturally ascending value, I would like my categories to be ordered. So that's what we're going to do next. Here we go. Well, we're not creating ordering yet, but we will get there. So the cut method allows me to take a column, numerical column in this case, and split it up into bins from 0 to 20, 20 to 40, 60 to 100. For the last bin, I just choose a value that's greater than any of the existing ages. And I can provide labels for each of these bins as well. Notice that I'm creating a new column here called age group. And so when I do that, I'll see that age group column in here. Let me do this. I'm going to copy and paste this cut function call into my code. And here we go. Okay. Doesn't look wonderful. I'm going to shrink my font just a touch here so that things will fit better. So instead of 34, let's go down to 39. All right, and now I can see everything on here. Okay, so if we do value counts on the age group column, and by the way, recall that you can just give a column name as an attribute as long as that column name does not contain any special characters or spaces. What we get told is that there are 3 people in the 20 to 40 range, 3 people in the 60 plus range, 2 in the 0 to 20 range, and 2 in the 40 to 60 range. Let's have a look at that. So here we are. Let me do that. df dot age group dot value counts. There we go. Now, if we look at this, notice here I've got a 20-year-old person who has been grouped into the 0 to 20 category. Well, what about this? What about this people who land on the boundary? When we do the cut, the default behavior is for the categories, for the intervals, to start just above the lower end of the what am I trying to say? Of the cut value, and go up to and including the upper cut value. Maybe we would rather have somebody who's 20 appear in the 20 to 40 group rather than in the 0 to 20 group. And there's a mysteriously missing slide here to create this age group lefty column. So let's see what got left out there. If I simply use cut again, and I'm going to create the age group lefty column now, what I can do is I can add an option right equals false. And that will eliminate the right-hand edge of the bin from being included within the bin. So I will now get from 0 up to but not including 20, and from 20 up to but not including 40, and 40 up to but not including 60. And here's my, now, okay, so now this is going to have, I'm going to run into font problems again. Let me anticipate that and just drop my font size down even a little more. And take a look at the revised data frame. Here we go. So now I've got the age group lefty column in here. And notice that the 20-year-old here is now included in the 20 to 40 group instead of the 0 to 20 group. Obviously, this is just a decision that you have to make whenever you bin your values like this for some kind of column. If I ask for the value counts now, df dot age group lefty dot value counts. Now I see that I've got 4 people in the 20 to 40 group, 3 in the 60 plus group, only 1 in the 0 to 20 group. Goodness me. We have a child employed by us. That might be illegal depending on where we are. And all of these people are making dirt for money. Interesting. Anyway, so that's how we adjust whether the cut value is included in the lower interval or the upper interval. Now, what if we don't know how many bins we're going to need? This data frame is, larger than the other little data frame that we were looking at before, but it's still relatively small. What if we're dealing with a data frame that has hundreds or thousands of rows? Then we're not going to be able to just glance at it and immediately know what the upper bound is on this thing. Fortunately, we can request a histogram of the ages. Once again, df.age is the same as df sub age. So let me ask for df dot age sub hist. And plt.show in idle. And here we go. Okay, and so now I can see on the histogram what the lower bound is, what the upper bound is, and I can also see the counts. And this, this can tell me that, okay, for this value going from 0 up to a little bit less than 100, I could go ahead and create 5 bins that are 20 wide, or I could create 10 bins that are 10 wide, or whatever I prefer. Let's take a look at some other nice-looking plots. This time we're going to use Seaborn, which I haven't demonstrated previously. Here is a Seaborn categorical plot. I'm plotting age on the y-axis, the vertical axis, versus age group on the horizontal axis. Seaborn is actually built on top of Matplotlib, but it has got a somewhat simpler interface, and it also tends to use a variety of colors. The idea of Seaborn is to make it easy to produce nice-looking plots, and I guess whether the colors are nice-looking or gaudy sort of depends on your own preference. But let's give this thing a try. So I'm going to say sns.cat plot, and the data is going to be from the current data frame. Y is going to be the age column, and X is going to be from the age group column. Let's do the age group lefty column instead. Age group lefty. And misspelled lefty. Oh, that's funny. All right, so lefty, age group lefty. There we go. Okay, and now I need to do my plt.show again in idle. Okay, and so what I see here is the actual age of the person on the vertical axis and the age groups in order on the horizontal axis. And I can see in the plot here that each of these points is at the location for somebody's actual age and which group that they belong to. So because I chose the age group lefty, I've got 4 people in my 20 to 40 group rather than having the 20-year-old appear down in the 0 to 20 group. Now, I did not get the colors that I was promised. And the reason for that is that I need to also specify which attribute here should be used as the basis for the coloring. So let me try this again. And I will say that I want the hue to be based also on the age group lefty value. And now when I do my plt.show, yay, I get gaudy colors. Okay, so blue, orange, green, red are the defaults that get chosen for this. Okay, so let's take a look at some other examples of Seaborn plots here. Here's a very similar kind of example, but in this case we're plotting age on the vertical axis, age group on the horizontal axis, and we're basing our hue off the gender of the people. I'm going to go ahead and just use age group rather than age group lefty for this case. Let's have a look. All right, so sns.cat. I should just copy and paste. Okay, once again, age vertical, age group horizontal. Hue is based on the gender, and I've got a semicolon that I don't need, but that's fine. And there we go. And now I will do the plt.show. Okay, and we see that the colors are based on the gender of the people. So I've got males and females in this particular plot. All right, here's another one. This time I'm plotting the hourly rate on the vertical axis, age group as before on the horizontal axis, and I'm asking for a box plot. My suspicion is that I'm going to need to specify the hue as well, but let's just try this as it is, first of all. All right. Yeah, so I just have blue as my colors. So let me base the hue on the age group. I don't need the semicolon. Copy that. And so hue is based off of age group. Okay, and so now I get my blue, orange, green, red colors. Next up, this thing is what's called a violin plot. Each of these images is supposed to be in the shape of a violin, sort of shaped based on where the actual values are. Here I have a single value, and so the width of the violin plot is not very wide. Here I have two values close together, so the width of the violin is wider in that case. And this goes off the right side of the screen, but I can, as we know, I can fortunately copy and paste this into my shell. Okay, so let's have a look here. So this time the vertical axis is the hourly rate, and the horizontal axis is the age group. I'm asking for a violin plot. I'm splitting the genders so that I've got male on the left side and female on the right side. Now, it happens that in each of these age groups, I only have either males or females, so I don't have any double-sided violin plots here. I'm using a pastel palette. I'm doing my hue based on gender, and I'm using sticks where the actual values occur. That's what these lines are. Each one of these lines is a stick indicating where the actual ages of the individuals are. All right, let's give this a roll. And show it. And there we go. All right, so this is a little bit vertically squashed compared to what's shown in the notes, but that's, I can just stretch up my my plot to make it look more like what we have in the notes. Now, if I use age group lefty rather than age group, I should have the 20-year-old show up in the 20 to 40 group rather than the 0 to 20 group. So let's give that a try. I'm going to copy this down. And I'll use age group lefty instead. And plt.show. Now, here we have only one male remaining in the 0 to 20 group, so there's not enough data to actually display a violin shape. Likewise, we've got one male that's now in the 20 to 40 group. Again, there's not enough data to display a violin shape. But if we had more data, we would end up having these nice violin shapes. Okay, now I just said nice violin shapes. So what is nice and what is distracting is somewhat in the eye of the beholder. I personally am not convinced that these violin plots are all that wonderful. I think the curviness of the shape, I'm not sure how much that really adds to understanding what's going on with the data. All right. Next up, here we have a bar plot. So let's give this a go, and I have a suspicion that I'm going to need to specify that the hue is based on gender, but let's give it a try as is. Okay. Yep, I need to have the hue based on gender. Whoops. Okay, and so there we are. Here we're doing a count plot. So this is just counting the number of occurrences of people in the different groups. Here I'm using age group rather than age group lefty. So I've got 2 people in the 0 to 20. And once again, I suspect I'm going to have to throw in the hue myself here. Give this a try. Well, let me not wait. Let me just do it. So I'm going to say that the hue is based on the age group. Okay, and there we are. All right, so that's just a quick look at some of the kinds of plots that we can get from Seaborn. You can, look up some documentation about Seaborn to find various other kinds of plots that it can create. It's up to you whether you think that these colors are pleasing or gaudy. That's it. Now, I do want to show a reference to a statistician who is meaningful to me. It's this fellow named Edward Tufte. I guess I need to shrink down this window. Okay, so there are competing views on how to produce good plots for statistics. And Tufte is at a sort of extreme minimalist end. He wrote a famous book years ago called The Visual Display of Quantitative Information, that was both very influential and widely criticized at the same time. So there are different schools of thought about how you go about creating good-looking presentations based on statistical data. I'll just leave it at that. You can check him out if that interests you.